Good evening, Lamai. Right, today we are going to discuss about the polarity of molecules. Right? Okay. So when we are discussing about the electricity concepts, right, we have discussed about the polarity of bonds, polarity of covalent bonds. Our major discussion today is about polarity of molecules. Right? Okay. For that, the polarity of bonds also matter, right? We'll discuss a bit about that thing, and then we'll move towards the major topic, right? The polarity of molecules. Right. First of all, let's discuss about the polarity of bonds, right? So we know there are two kinds of covalent bonds are available, right? What are two kinds? Polar covalent bonds and the non-polar covalent bonds, right? So polar covalent bonds. See how they are formed. Polar covalent bonds. Right? When the connected two atoms, the participating two atoms in a covalent bond are with two different electronities. As example, let's take the HCl. So electronity of hydrogen is 2.1, the electronity of chlorine is 3.1. So the two guys are with two different electronities. So what will happen? So then the shared pair of electrons is actually now not at the center, because greater the electronity means you are attracting the electrons more, the electronic pair more than the atom with the lower electronity, so that the bonded pair will be attracted heavily towards the chlorine in this case, because chlorine is with a greater electronity than the hydrogen, so that the two electrons will occupy like this in the space between the H and Cl. Those are not at the center, right? So we can say, right, there will be a high electron density, higher electron density at the chlorine side and bit lower electron density at the hydrogen side when considering this bond, because the electrons are more towards the chlorine in this case. So the charge on the chlorine is bit more negative than the charge on the hydrogen. So we can say it is slightly negative charge, and this one is slightly positive charge, right? So we can think of a polar bond making by this kind of a situation. So there is a covalent bond, right, with some poles, with some negative pole as well as a positive pole, right? So we can denote the same scenario. We can picture the same situation with this kind of a picture. So electron pair is more towards the chlorine, not symmetric, but more towards the chlorine like this. The shared pair is more towards the chlorine. Density here is very high and density here is very low, right? So that the chlorine's terminal is negatively charged and hydrogen's terminal is slightly positively charged. This kind of a bond will be referred to as a polar covalent bond. Polar covalent bond. So with this covalent bond, you are with some poles, positive pole and a negative pole, right? That is a polar covalent bond, right? So normally we denote that polarity of a covalent bond with these delta signs. Delta mean a slight charge increasement or slight charge decreasement, a slightly positive charge and slightly negative charge. So these are the polar covalent bonds, right? So let's come up with some other examples. So NH3, with NH3 also you will see such kind of polar covalent bonds. See, this is NH3 molecule, right? Your electrons are more towards the nitrogen in this case, because nitrogen carrying some greater utility than the hydrogens, right? So electron pairs are greatly attracted towards the nitrogen. So that nitrogen comes up with a slightly negative charge and hydrogen will come up with a slightly positive charge. So you can denote the polarity of these bonds with the use of these deltas. In this case as well, right, nitrogen carrying some negative delta and hydrogen will carry some positive delta. So we are referring to polarity of bonds with these delta signs, right? So let's take a look at another molecule like H2O. The bonded electrons are heavily attracted towards the oxygen, so that we can come up with the polarity as negative delta for oxygen and positive delta for hydrogen. So basically, when denoting the polar covalent bonds, relatively electronegative atom gets a negative delta, while the electropositive atom gets a positive delta, right? That is how the polar covalent bonds are, right, marked, right? Okay. So here the oxygen is with 3.5 electronity, hydrogen is with 2.1 electron. That is why the polarity appears like this, right? So these are referred to as polar covalent bonds, right? So let's go to the note line. See, it says when the two atoms participating in a covalent bond are different in electronicities, the bonding electron pair has a higher probability of being found closer to the more electronegative atom. In such a situation, the bond is considered as a polar covalent bond. You clearly see the situation here. So there's a space there, so you can write this thing, the first line, right? The polarity of HCl bond. You can write like this, right? Okay. Then it says polar covalent bond is polarized such that a negative pole on the electronegative atom and a positive pole on the electropositive atom. See, in this bond, polar covalent bond, you have a positive pole at the electropositive atom and negative pole at the electronegative atom, right? So polar covalent bonds have some ionic character. So polar covalent bonds are with some ionic character. Let's see what it means. Lamai, chemical bond means a method of connecting masses, right? If I ask you to give the simplest definition, simplest general definition for a chemical bond, you should say that it is a method or way of connecting masses, right? In a covalent bond, the shared pair of electrons will connect the two masses. The shared pair of electrons is responsible for the connecting masses. In an ionic bond, the shared pair, the opposite charges in an ionic bond, the opposite charges are the reason for the attraction of those masses, right? Those are the major two kinds of primary bonds, no? The covalent bonds and the ionic bond, right? Again, I'm telling you, in covalent bonds, right, way of connecting masses is like this, no? In a covalent bond, you have the two nuclei of atoms, right, and a shared pair of electrons in between. See, then what will happen? The shared pair of electrons will attract the two nuclei towards it, attract the two nuclei towards it, so that these two nuclei will be connected by the shared pair of electrons. So actually, almost all the mass of the atom resides in the nucleus. So the two masses, the two nuclei, will be connected by the shared pair of electrons. That is what is meant by a covalent bond. And when it comes to an ionic bond, what it does? So see the ionic bond in NaCl. So Na plus and Cl minus. Those two particles, those two masses are attracted here by the opposite charges. So the way of connecting masses is actually by attracting the masses by electrostatic attractions of two opposite charges. That is what referred to as the ionic bond. This is referred to as the ionic bond. Attraction of masses by the opposite charges. This is covalent bond. Attraction of masses by the shared pair of electrons. Shared pair of electrons. Right? Those are the major two types of primary bonds. Right? So when it comes to a polar covalent bond, right, you clearly see the two masses, the hydrogen and chlorine, are attracted or are connected by a shared pair of electrons. So that is the covalent character of this polar covalent bond. And not only that, these two atoms, the hydrogen and chlorine, are now attracted by the opposite masses as well. Due to these opposite masses, these guys will attract to each other. Right? So that is the ionic character. Attraction of masses due to the opposite charges of them. So ionic character. So when it comes to polar covalent bonds, the masses are attached by the shared pair of electrons as well as the opposite charges. So the covalent character as well as the ionic character, both are there when it comes to a polar covalent bond. But that is what it says. The note says, so polar covalent bonds are with some ionic character. Yes, those are with some ionic character. Right? Okay, the thing is clear now. So some other examples are also given. So you can draw these two structures as well at the space given, at the second space given in your note. Right? So basically when we are denoting the polar covalent bonds, so the electronegative atom gets a negative charge while the electropositive atom or the least electronegative atom will get a positive delta. That is how a polar covalent will be marked. Right? So you can draw these two pictures as well at the space given, the second space. Right now. So then we can say higher the electronegative difference, right, of the two atoms, greater will be the polarity. Right? So if you need some example, right, we can say, right, so higher the electronegative difference, that means delta x, higher delta x, the electronegative difference, higher will be the polarity of the covalent bond. Higher the polarity means higher will be the ionic character. Higher the polarity means higher the ionic character of the covalent bond. Right? Okay. If you need an example, we can write like this. So when it comes to HCl, what is the difference? This is 2.1 and this is 3.1. So the difference, the delta x can be written as 1 unit. 3.1 over 2 minus 2.1. When it comes to HF, the difference is between these two guys are 2.1. The electrons are 2.1 and the 4.0. So the difference of electron is actually 1.9. So greater your electron difference in this case than here. So what we can say is the two electrons here are more towards the halogen than here. Right? Yes, this could be the center. This could be the center. But here the electron pair is more towards the halogen. Right? So greater negative nature at the halogen side in this case than this case. So greater polarity will appear when the heat difference is high. That is the idea, right? Greater the heat difference between the two atoms which participate in the covalent bond, greater will be the polarity which will create. So greater will be the ionic character as well, right? Okay. So it is better to mention these two pictures as well at this phase. Right, no? Okay. Let's discuss about the non-polar covalent bonds. We have just completed the discussion about the polar covalent bonds. And let's go towards the non-polar covalent bonds. There are two types now. Polar covalent bonds and the non-polar covalent bonds, right? Okay. Let's discuss about the non-polar covalent bonds, right? Non-polar covalent bonds, right? So I'll give you example. The I2 is a good example. So in I2 molecule, right, as the two atoms connected are with the same eternity, two atoms connected are with the same eternity. So the bonded electron pair will be shared evenly by the two atoms. No one will attract heavily the electron pair. Both share evenly the two electrons. So those will occupy the center of the two internuclear distance. Right? So one can picturize this situation as a symmetric electron arrangement between the two nuclei of the atoms participating in the covalent bond. So symmetric electron distribution as the bond. Right? So this is the situation with the non-polar covalent bonds. Non-polar covalent bonds. So no polarity will be created. There's no area with a greater electron density, and there's no area with a limited electron density, which can be seen in here, but it is not here. Right? Okay, so symmetric electron density with the covalent bond and no poles appear. So non-polar covalent bonds. Right? So these guys are not with any kind of ionic character. Right? The bond is totally due to sharing pair of electrons. The way of connecting masses is totally the shared pair of electrons. So 100% covalent. Right? This can be referred to as 100% covalent. No ionic character in these non-polar covalent bonds. Right now? So at the space given, you can do this stuff as well. Right? Okay, those are the non-polar covalent bonds. Right? Clear now? Right. Now we'll discuss about the dipole moment. Right? We'll discuss about the dipole moment. Our next topic is the dipole moment. Right? I'll discuss the background about the dipole moment. Right? Now when it comes to these polar covalent bonds, right? Different polar covalent bonds are with different kind of polarities now. Earlier we had seen when it comes to HCl and HF, the HF is more polar than the HCl. Right? So OH bond will be more polar than the NH bond. because the electron difference is higher with the OH bond than the NH bond. So it comes to a polarity of a bond. Different kind of polar bonds are with different magnitudes or different strengths of polarity. So the strength or the magnitude of polarity is actually given by a parameter called dipole moment. So dipole moment is kind of a vector which is used to express the polarity of the bond. So it will give you the magnitude of the polarity of your bond, of your polar covalent bond. That is why we need a parameter called dipole moment. Right? So in your note it is said the magnitude of the polarity is measured by a parameter called dipole moment. Right? Okay. So let's copy the equation. Let's copy the equation for the dipole moment, right? So this is about the dipole moment. Dipole moment. Dipole moment is a parameter used to measure the polarity of the bond, right? Polarity of polar covalent bonds will be measured by a parameter called dipole moment. Right? Dipole moment. So it will be given by this equation. So dipole moment of a copolar bond is equal to the charge appearing on one terminal on one atom multiplied by the bond length of the two atoms participating in bond. With this, you are able to come up with the dipole moment. In symbols, we can write the mu. The mu is a symbol used to express the dipole moment is equal to delta R. Delta is the charge appearing on one atom, the positive delta and the negative delta, and R is the internuclear distance, or one can say the bond length. This is the equation we are using to come up with the magnitude of the dipole moment. Right now, the magnitude of the dipole moment is given by this equation. Right? We'll do a little calculation. Right? First of all, just write the equation now. Charge on an atom or charge on one pole into bond length mu is equal to delta R. Right? Okay. Then another thing we should know. What is that? The dipole moment is referred to as a vector. Dipole moment is referred to as a vector. What it means? Vectors. So basically vectors are parameters with a measurable value as well as a direction. Right? Vectors are parameters, right, with some measurable value, magnitude, and a direction. So for some parameter to become a vector, it should have magnitude and a direction, right? So the magnitude will be calculated by this equation. Then how come the direction? Let's discuss about that thing. the direction of the dipole moment. It is very simple. So if you are to take the HCl, you take the HCl bond, so you have a positive terminal and a negative terminal. So the direction of the magnitude will be marked in this vector, the dipole moment, as marked by a arrow. Basically, the directions of the vectors will be marked by arrows, where the arrow head towards the more electronegative atom or the negative pole, and the arrow tail towards the more electropositive atom. So basically, it will be denoted by a simple positive sign like this. This is the way of marking the dipole moment in a polar covalent bond, right? Arrow head towards the electronegative atom or the negative pole of the polar covalent bond, and the tail towards the right the positive terminal or the positive delta terminal, or the right least electropositive atom, electronegative atom, or the electropositive atom, positive thing towards the electropositive atom, right? The head towards the electronegative atom. This is how the dipole moment, the direction of the dipole moment, will be indicated for a polar covalent bond. For a polar covalent bond. See, for some others, right? If you take some H2O, see how to denote the dipole moments of the two bonds appear in there. So you know this is the negative pole and this is the positive pole. This is the high affinity atom, this is the electropositive atom. So dipole moment will be marked like this. Arrow head towards the negative atom and arrow tail towards the electropositive atom. So for this bond, it will be marked like this. This is how to mark the two directions of the dipole moments of two OH bonds. Right now? Okay? Always the positive thing, the arrow tail towards the electropositive atom and the arrow head towards the electronegative atom. So that will give you the direction of the dipole moment, this arrow. So normally the directions of the vectors will be given by the arrows, no? Arrow heads, no, right? So the same as that, right? So you can draw these two as well at the space given. Here it says dipole is denoted as an arrow, right? And the arrowhead is pointed right towards the negative pole of the molecule. Sorry, arrowhead is pointed towards the negative pole of the atom, negative pole of the covalent bond. Right now, got the idea? So that is how you are supposed to symbolize the dipole moment, the direction of the dipole moment. Right? Okay, the magnitude will be given by this equation, and the direction will be given by this kind of arrow pointing towards the negative pole of the covalent bond, starting from the positive pole, electropositive atom to electronegative atom. Right now, got the idea? So that is what you should know about the dipole moment, the magnitude, and the directionality. Right now? Okay. So then the book says this dipole moment data actually can be used to calculate the percentage ionic character of a covalent bond. See, earlier when we are starting discussion, we had said that polar covalent bonds are with some ionic character. So the percentage ionic character can be calculated with the use of this dipole moment data. Let's see how to do so. How we are able to do so. How to calculate the percentage ionic character with the use of dipole moment data. Let's examine that. Right? So dipole moment data can be used to calculate the percentage ionic character of a polar covalent bond. Let's see how. I'll come with example. Right. Let's calculate the percentage ionic character of HCl. Calculating the percentage ionic character of HCl bond. Let's see how to calculate this thing. First of all, we should know the bond distance, the practical data for the bond distance and dipole moment to do this calculation. Let's say they are given the bond distance as 127 picometers and the practically calculated dipole moment as 3.45 into 10 to the power minus 30. Right? Dipole moment will be given by Coulomb meters, right? Charge into distance, no? Charge on an atom into the bond distance, no? Coulomb. Charge will be given by Coulomb and distance will be given by meters. Coulomb meters is the SI unit for dipole moment, right? So this thing is there in your note, right? That question is there. They are asking if the bond distance and dipole moment are given for the HCl. They have asked you to calculate the percentage ionic character, right? Let's do the summation then, right? These are given, no? Right. With the use of bond distance, first of all, we can calculate the charge on an atom. So calculating the charge or the partial charge delta on an atom. You know, the HCl is like this, no? The HCl is like this, huh? So you have partial charges on atoms as the bond is polar. So we can come up with this delta by applying the dipole moment equation. The mu is equal to delta R, then the delta is equal to mu over R. Delta is equal to mu over R. Delta is equal to mu over R. Let's apply that thing. The mu value is given as 3.45 into 10 to the power minus 30 and the R is the bond distance, so it will be 127 pico means 10 to the power 12 to the minus 12 meters. So if this kind of unknown thing is to consider, unknown equation is to consider, always substitute with the SI units. Always substitute the SI units. The distance, the SI unit is meters. So always substitute the SI units, then you will get the answer in SI units as well, right? If you have to simplify this stuff, we'll come up with the answer like this. It will be 2.27 into 10 to the power minus 20 coulombs. So that is going to be the charge on an atom. It's going to be the charge on an atom. This charge. So now we are going to use this charge on an atom to come up with the percentage ionic character. Come up with the percentage ionic character. Right? Let's come up with that. Number 2, calculating the right percentage ionic character. Now, to calculate the percentage ionic character, there is a equation. There is a equation. The percentage ionic character is equal to actual charge on an atom, actual charge on an atom, that means the charge actually appearing on an atom, that is the delta, divided by charge on an atom, charge on the atom if the bond is 100% ionic. Charge on your atom if the bond is 100% ionic into 100. Right? This is the equation we are supposed to use to calculate the percentage ionic character. Let's use this to copy the percentage ionic character. Right? First of all, let's copy the charge on the atom if the bond is 100% ionic. We have calculated the delta charge now. That is done. So before coming up with the ionic character, we should know the charge on the atom if the bond is 100% ionic. Let's calculate that. Let's calculate that here. Right? So I'm calculating that thing here. Right? If the bond is 100% ionic, that means if it is like this, if the HCl is like this, if the bond is 100% ionic, right, then the charge on an atom, is equal to what? 1 unit is equal to 1 unit. So one can write 1 into the smallest charge unit. The actual charge is not 1 llama here. The actual charge is not the +1 and -1. No. That is a relative charge. No. The actual charge is 1 into the electronic charge. Here minus 1 into electronic charge. That is the actual charge, right? That is what we need, the Coulombic charge, not the relative charge, right? Okay. So we can write charge on atom is equal to 1e. 1e means 1 into the smallest charge unit, which is 1.602 into 10 to the power minus 19 coulombs. Let's write it as 1.6 into 10 to the power minus 19 coulombs. So that is the charge on an atom if the bond is 100% ionic. So now we know the delta charge and we have calculated the charge on an atom if the bond is 100% ionic. So now we can come up with the percentage ionic character. So percentage ionic character is equal to the delta charge, the actual charge appearing on an atom, that is this value. Yes, we have calculated, right? 2.27 into 10 to the power minus 20. And the charge on an atom if the bond is 100% ionic is this amount. right? That is just, we can write 1.6 into e to power minus 19 coulombs into 100. So simplifying this thing will give you 17%. So this is the percentage ionic character of HCl, bond, the bond between the H and the Cl in HCl. This is the percentage ionic character. 17%. 17%. So when it comes to HCl bond, 17% is due to the ionic nature or the charged nature of the two atoms, and the rest, the 83%, belongs to the covalent nature. So the bond between HCl is composed of 83% of covalent character and 17% of ionic character. That is the idea here, right now. So you can complete the calculation now, and then we can move on. Just complete this stuff. Right. So far we have discussed about the polarity of bonds, right? The polarity of covalent bonds. That was the discussion so far. Now we are moving towards the polarity of molecules. That is the major topic today. As our topic says, this is about the polarity of molecules, right? To consider the polarity of molecules, not only the electronegativity values or the electronegativity difference, but also the geometry matters. The geometry of the molecule also matters, right? So let's discuss about this thing, the polarity of molecules. Let's start with the non-polar molecules. Right. The idea is this, right? So here the polar nature means the asymmetric nature of the electron density. That is what we meant by the polar situation. Non-polar means your electron density is symmetrically distributed. Like this, no? So when it comes to HCl and HI, that is what we have seen. No? When it comes to HCl, the electron density is actually asymmetrically distributed. That is why kind of polarity appears. When it comes to I2, the electron distribution is symmetric. So no poles appear. So this can be denoted using the arrows as well. So if you have to think of the dipole moment, when it comes to polar bonds, you have a dipole moment. But when it comes to non-polar bonds, you don't have such. No dipole moment will be marked. But here, dipole moment will be marked. If you have marked and got a dipole moment, you can say the arrowhead is the terminal with a negative nature, and here, this is the terminal with a positive nature. So with something, let's say you have a species, right, where A and B is with a bond, and the dipole moment is marked like this, then we can say this guy is the positive terminal of the bond and this guy is the negative terminal of the bond. The two guys are with a kind of electronegativity difference, and this is the electropositive atom and this is the electronegative atom. All the things can be tell by seeing just only the direction of the dipole moment. If dipole moment is not appearing with a molecule like this, we can say there's no such poles and the electron distribution is symmetric. That is the whole idea here, right? So we can use those same ideas to come up with the polarity of molecules, right? So if with the molecule, if with the whole molecule, there's no such dipole moment thing appearing, then we can say it's a non-polar molecule. If some dipole moment appears with the molecule, you can say it's a polar molecule. So this is regarding the dipole moment of the molecule. So basically, as molecules are with more than one covalent bond, as molecules are with few covalent bonds, could be with few covalent bonds, so that we have to take the resultant dipole moment as the dipole moment of the molecule, right? So dipole moment of the molecule means that is the resultant dipole moments of each and every bond, right? So as the molecules are with few covalent bonds, the dipole moment of the molecule means it is a resultant dipole moment of each and every bond appearing with the molecule. So first of all, we have to come up with the resultant dipole moment of the molecule. Then we can decide the polarity of the molecule. If the resultant dipole moment, right? That means vector addition of all the dipole moments of all the bonds in the molecule, in the species, that is the resultant dipole moment, right? If that is 0, then we say no dipole moment with the species. That means those are non-polar species. Then those species are referred to as non-polar species. That is the definition. That is the definition. If the resultant dipole moment is 0 for your considering molecule or considering species, then such things are referred to as non-polar species. See some examples. BeCl2. BeCl2. See BeCl2. BeCl2. What happens here? So dipole moment of this bond can be marked like this. The arrow head towards the electronegative atom, tail towards the electropositive atom, positive spin towards the electropositive atom. With this bond, you can mark like this. And the two dipole moments are equal with equal magnitudes because both are with the same between same two atoms. These two dipole moments are equal with magnitude and opposite with the direction. Equal magnitude, opposite with the direction. So such vectors will cancel off. When you do some addition of vectors, such vectors will cancel off. Vectors with equal strengths, equal magnitudes, and opposite, those will cancel off, ultimately giving you a zero net dipole moment. So this molecule is non-polar. Right? So another example. boron chloride. See, again, the electrons are attracted towards the more negative atom, fluorine. Here, also we can denote the dipole moment like this. Right? Electrons are going towards the fluorine. So this is the positive terminal and this is the negative terminal. The negative atom gets the negative terminal, arrow head. The positive atom gets the positive terminal, arrow tail. So what will happen? When it comes to resultant, right? These three things will cancel off now. When it comes to resultant, those will cancel off. So it's a planar molecule like this now. The stuff is kind of a planar molecule like this now. With 120 angles each between the bonds, with 120 angles each. So what will happen? So basically, with this kind of a planar molecule, right, the horizontal resource will cancel off. So if you are to take the bond between these two, you will take a half of the bond here, right? It is 60, and yeah, it is 60 degrees, right? So this is this resolve, horizontal resolve gives you, if this is x as the magnitude, x sine 60. We are dividing it with 60 each angle. So this is x sine 60. And here as well, the horizontal resolve will be x sine 60. So those will cancel off. Those will cancel off. What about the vertical resolve? So from this dipole moment, it comes x cos 60. Here as well, another x cos 60. So 2 into x cos 60. Cos 60 is half. So 2x into half is just x. That x will cancel off with this. Right? So if you need to draw the same thing here, like this, no? So you can resolve this one, no? These ones, no? So you can think of resolving these vectors. Right? The two horizontal resolves of this thing, sorry, the two vertical resolves, in this case the vertical resolves, the two vertical resolves of this thing will be this 60, as this angle is 120, no? So two vertical resolves means it is, if this is x as a magnitude, this is also x, this is also x as a magnitude, because those are same kind of bonds between same two kind of atoms. So this value, the vertical resolve of this bond is x sine 60, and here as well x sine 60, right? So these two things will cancel off, 2 of x sine 60. Then what happens to this resolve, right? Towards this, it will be a x cos 60. From this one as well, another x cos 60. So 2 of x cos 60. The horizontal resolve. So you can write 2x cos 60 is half. This is just x. So to this side, the magnitude x comes, and that x will cancel off with this x, right? So the two things will cancel off. So vertical resource will also cancel off, as well as the horizontal resource. Horizontal resource will cancel off with this one, so that the net vector is equal to 0. Net vector is equal to 0. So we can write the dipole moment is 0. The net dipole moment is 0. The resultant dipole moment or the net dipole moment is 0 for BCl3, so that it is non-polar. Right? It is non-polar. No resultant dipole moment appearing with the BCl3. It's non-polar. See some other example. Let's come up with some other CH4. CH4. What will happen with this thing? So when it comes to CH4, we can think of that tetrahedral shape. We can think of the tetrahedral shape like this, as a shape with two V shapes. A shape with two V shapes, right? Two V's. One V is appearing here, and another V is appearing here. Two V shapes, no? See, one V and another V. This is tetrahedral, right? This is just tetrahedral, no? We can count the tetrahedral, right? This tetrahedral thing can be seen like a combination of two V's. Then what will happen? Right? This can be referred to as summation of two V's. Two are in the same plane, and the other two, one into the board, and other is actually outwards from the board. Right? So what will happen? So basically, right, vertical resource will cancel off with these guys. So these are the dipole moments to mark, no, with the 4 bonds. So basically, horizontal resource will cancel off. The two each other will cancel off their horizontal resource. And for the vertical resource, one will give you, the upper two will give you this kind of vertical resolve, and the bottom two will give you this kind of vertical resolve. So those will also cancel off. Right? Those will also cancel off. So net dipole moment is going to be 0. So net dipole moment is going to be 0. It's non-polar. So CH4 is kind of a non-polar molecule, right? So you have to, if you have to think of that thing, no, it's non-polar. This is the situation, no? Two E's, this is two E's. So the vertical resource like this and this, so vertical resource will cancel off each other. Here as well, for these two guys, the vertical resource, this and this, those will cancel off. For this, it is this and this. And it comes to, those are the horizontal resource, those will cancel off like this, for these two, like this. Right? When it comes to vertical resource, these two guys will produce a vertical resource like this, and these two guys will produce a vertical resource like this. So those two will also cancel off, as as all the 4 bonds are equal resource, up and down will cancel off. Horizontal things will also cancel off. Right? Okay. So that is how the CH4 comes up with a 0 net dipole moment. So it is non-polar. So basically, when you are with no lone pairs with your central atom, and when all the bonds are equal, all the connected groups are equal, and you are not with any lone pair with your central atom, then with such situations, always the resultant dipole moment becomes 0. All the resources of vertical and horizontal resources will cancel off, and ultimately you will come up with a 0 net dipole moment. If your center atom is not with lone pairs and when all the connected groups are same. Right? Normally such kind of shapes are referred to as perfect shapes. What are the perfect shapes? When you have with no lone pair in your central atom, and when all the connected groups are the same. Such shapes are referred to as perfect shapes. When you are referring to a perfect shape, definitely the net dipole moment becomes 0, and those are referred to as non-polar situations, non-polar species. Right? Let's come with some more examples. Right? See the PCl5. See the PCl5. There is another example. See, when it comes to PCl5, right? This is how it appears now. So these two dipole moments, the up and down, you remember the shape, right? PCl5, that fan shape, that fan trigonal bipyramidal. The up and down, the two dipole moments will cancel off first, and then dipole moments of this plane, the same plane, the blades of the fan, those will also cancel off like this. In this manner, the three dipole moments, these three dipole moments will cancel off, as these two are linear with opposite directions and same magnitude. Those will also cancel off. So the net dipole moment will be 0 there. So that is also non-polar. If your molecule is with 0 net dipole moment, that is going to be non-polar. So basically all the perfect shapes comes up with non-polar situation. So discuss about the XCFO. Sorry, before that, let's come with the SF6, the octahedral situation. You have 4 bonds at the same plane and 2 bonds above and below. So what will happen? Here as well, first you can mark the dipole moments with each and every bond. See, electronic negative atom gets the arrow head, while the electropositive arrow get the arrow tail, which is with a positive sign as well. So when it comes to this, you clearly see the up and down, the 2 bonds will cancel off. First of all, the 2 dipole moments will cancel off, the up and down, and then these two are with opposite sides, cancel off. These two are with also opposite directions, those will also cancel off. So all the 6 dipole moments will cancel off, as those are with same magnitude and opposite directions, right? So net dipole moment is going to be 0, so it is also non-polar. So all the perfect shapes are non-polar. These perfect shapes are non-polar. What are perfect shapes? Perfect shape means when your central atom is not with a lone pair and all the connected bonds are same. Those are referred as perfect shapes. All the perfect shapes are non-polar. Right now? Okay. Even not being a perfect shape, till you can be non-polar. What I have said. All the perfect shapes are non-polar, that is okay. But even you are not a perfect shape, even you are not carrying a perfect shape, till you can be non-polar. All the perfect shapes are non-polar, that is okay. Even though you are not carrying perfect shapes, till you can be non-polar. Till you can be non-polar. See, how come? I'll give you another example. Another example. Non-polar molecule without a perfect shape. XCFO. Some square plane structure coming from the octahedral electromed geometry. See, even this one is non-polar. Why is that? These two dipole moments will cancel off, as well as these two. So these two will cancel off each other, as well as these two. So the dipole moment is going to be 0. So it is also non-polar. So what we have said is all the perfect shapes are non-polar, and sometimes even without a perfect shape, still you can be non-polar. Anyway, what should be the requirement to fulfill for a molecule to become non-polar? It is the resultant dipole moment. The resultant dipole moment should be 0. Resultant dipole moment means the vector addition of each and every dipole moment of the species. Vector addition of dipole moments of each and every bond in your molecule is referred to as net dipole moment. If that is 0, then your species is referred to as a non-polar species. Non-polar species. And these non-polar species are also referred to as symmetric molecules. Symmetric species. Because non-polar means you don't have a negative pole or a positive pole. Non-polar means you don't have a negative or a positive pole. That means you don't have a area with great electron density, or you don't have an area with small electron density. Negative pole means you are with an area with great electron density. Positive pole means you are with an area with small electron density. So no negative pole, no positive pole means you don't have such areas in your chemical species. That means your electron cloud is symmetrically distributed. So non-polar means your electron cloud is symmetrically distributed, so that they can be referred to as symmetric molecules, symmetric species. So all the non-polar molecules can be referred to as symmetric molecules as well. Right now? Got the idea? Right. That is all about the non-polar molecules. Right? That is all about the non-polar molecules. Let's discuss about the polar molecules. The polar molecules, right? Polar molecules. One can have polar species. The definition is if the resultant dipole moment, that means the vector addition of dipole moments of each and every bond of species is not equal to 0. Then such a species is referred to as a polar species. Referred to as a polar species. Let's get this idea with an example. Let's take the NH3. NH3. Right? First you have to first you have to draw the NH3 with the correct shape, right? That is very important. No? To decide the dipole moment of a bond, first you have to draw it with the correct shape, right? NH3. Okay? Right. Then mark all dipole moments. mark the dipole moments of each and every bond. So basically, the NH electrons are going towards the nitrogen, right? Nitrogen is more electronegative than the hydrogen. So electronegative atom gets the arrowhead, positive atom gets this arrow tail, the positive pole. This is how the dipole moments are normally marked. So you clearly see the vertical resource will cancel off as the three things will appear like this, right? As the three things will appear just like this, right? Just like this, right? The vertical resource definitely will cancel off, but not the horizontal resource. So horizontal resource won't cancel off, will appear ultimately as a net dipole towards upward. So this is not going to be equal to 0, right? The net dipole moment will appear towards upwards ultimately. So NH3 is non-polar. NH3 is non-polar. Right? Let's come up with another example. Some other example. H2. Another example. For a polar species. See? These are the dipole moments of bonds. So the horizontal resource will cancel off, but not the vertical stuff. Horizontal resource will cancel off, but not the vertical stuff. So you will see kind of a net dipole or net vector going upwards. So net dipole moment is not equal to 0, that is polar. So sorry, here also polar, right? Net dipole moment is not equal to 0 means it is polar. Sorry for that, right? Right? So that is how it looks like. So any species carrying a net dipole moment is referred to as a polar species. That is also polar. Right? Got the idea? So decide the polarity of a species. First, you need definitely to come up with the shape of the molecule. Then you have to mark the dipole moments of each and every bond, each and every covalent bond. Then you have to take the resultant dipole moment, resultant of the all the dipole moments. So if the resultant dipole moment is 0, such a species is non-polar, and if the resultant dipole moment is not equal to 0, such a species is polar, right? So these are the polar species, right? So when it comes to polar species, we should be able to comment where the positive pole appears and where the negative pole appears with the molecule, right? If you comment that, let's see. So basically, when it comes to this, you can draw the resultant vector like this. This could be the resultant vector, right? This could be resultant vector. So the summation of these two will appear like this. This could be the resultant vector, right? So with the use of resultant vector, we can come up with the two terminals, the negative and the positive poles of the molecule. So the arrowhead is towards the negative pole, arrow tail is towards the positive pole. So when it comes to H2O, it's a polar molecule. Where your negative pole appears on the oxygen and the positive pole appears at the exact center of the two hydrogen atoms. Your negative pole appears at the oxygen and your positive pole appears at the exactly the center of the two hydrogen atoms. That is the polarity of H2O. You have greater electron density here at the oxygen pole, and you have slightly less electron density here. Some asymmetric electron cloud with greater electron density on the oxygen and some limited electron density on the space between the two hydrogens. That is the polarity of H2O. When it comes to this one, see, as net dipole moment is not equal to 0, it's a polar molecule. It's a polar molecule. And what is the negative pole and what is the positive pole? Right. So when it comes to these, as the horizontal things cancel off, when it comes to a net dipole moment, it will appear like this. Vertical things towards upward will appear like this. So this says your positive put terminal is between these hydrogens at the center of the three hydrogens, and the negative terminal is on the nitrogen. That is the polarity of the NH3. Your positive pole is between the three hydrogens, and your negative pole is on top of the nitrogen. So you have greater electron density here on the nitrogen and slightly smaller electron density at the center of the three nitrogens. So the center of the three hydrogens. Right now, that is how the NH3 looks like. So it's a kind of an asymmetric electron density. It's asymmetric electron distribution. Sorry, asymmetric electron distribution. Right now, that is what it means as a polar molecule. Right. Okay. Right. Few more things. Right. To learn about this polar molecules. Right. This is just how you're supposed to decide whether a species is polar or non-polar. Just take in the resultant or the net dipole moment. Right. Okay. Let's discuss a bit more about this polar stuff. Right. Let's try to compare the polarities of NH3 and NF3. That is our next concern. Right? We are trying to compare the polarities of NH3 and NF3. So here, comparison of polarities of NH3 and NF3. These are also important stuff, right? Comparison of polarities of NH3 and NF3. Let's see. The idea is this. So, right, I'll write the NH3 first, right? This is the NH3. This is the NH3, right? You have the lone pair as well, huh? You have the lone pair as well, small lone pair. And this is your NF3. Right, you can mark the dipole moments of NH3 like this. Your positive pole towards the hydrogen and negative pole towards the nitrogen, because nitrogen is more reactive than the hydrogen. In this case, you can mark the dipole moments like this. Your positive pole towards the nitrogen and the negative pole towards the fluorine. Why is that? Fluorine is more reactive than the nitrogen. This is 2.1 no. This is 3.1 no. So 3.0 no. Sorry for that, right? Then the actual number is 3.04. This guy is 3.04. This is 4.0. So when it comes to delta value, of these bonds, that could be the more or less the same, because the difference between the nitrogen and hydrogen is actually 0.96 units. The difference between the nitrogen and fluorine is actually again right? 0.96 units. Here the 0.94 units. Here the 0.96 units. So the delta x, the difference is not that much considerable, right? So we can take the delta values are the same. Space of delta values are z with the NF bond as well as the NH bond. Magnitude of a single dipole moment can be referred to as same for the NF and the NH, right? The bond distance is not that much, right? Then what matters here is the effect of lone pair. Effect of lone pair. When deciding the polarities, the strength of polarities, which one is with a greater polarity than the other, the major concern here is the effect of the lone pair. Effect of the lone pair. What happens there? The point is this. Lamai, if you are to consider kind of a symmetric orbital like this, atomic orbitals which are symmetric, you have to consider these symmetric orbitals. We say they won't possess a dipole moment. They won't possess a dipole moment. That means they are not with a asymmetric nature with the electron distribution. When it comes to atomic orbitals, their electron distributions are even. The two lobes are even. Electron distributions are even. So that symmetric electron distribution is there. So no appearance of dipole moment with the atomic orbitals. But when it comes to hybrid orbitals like this, the hybrid orbitals, the two lobes are with two different sizes. Electron densities are not that symmetrically distributed. So you have the nucleus here. So you clearly see, you can mark the two electron distributions like this. This is the area with higher electron density and this is the area with lower electron density close to the nucleus. This could be marked like this. So after cancelling of some extents of this dipole moment, it will come up with a small dipole moment like this towards upwards. But here these will cancel off, no? This one will be equal to this one. So that these two things will cancel off. But not here. So you will come up with a little dipole moment appearing with the hybrid orbitals. Right? In S orbitals also you won't see such, right? So dipole moments here will cancel off the one with the here. So symmetric with symmetric orbitals, the atomic orbitals, dipole moments won't appear. But when it comes to hybrid orbitals, right? You will see the appearance of a dipole moment because the asymmetric electron distribution. So that can be marked here. You can mark that effect of lone pair like this. It is comparatively small. It is comparatively small compared to the dipole moments of the bonds, right? It's comparatively small compared to the dipole moments of the bonds, right? So here also a small dipole moment appears with the lone pair. It is actually outward from the nucleus, right? It is actually outward from the nucleus. Outward from the nucleus. Dipole moment of the lone pair is the nucleus. It is outward from the nucleus here as well. Right? That is the effect of dipole moment by the lone pair. Right? Now let's come up with the resultant dipole moment. Right? Normally in vectors, the magnitude will be given by the length of the arrow. Direction will be given by the direction of the arrow in vectors, and the magnitude will be given by the length of the arrow in vectors. Right? Let's consider the length of the arrows to come up with the magnitudes of these, magnitude of the net dipole moments of these two guys. First copy this one. So with the bonds, there will be a net dipole moment towards upwards with the bonds, with the 3 bonds. When it comes to this one, with the 3 bonds, there will be net dipole moment downwards. So those will be more or less the same with the lengths. With the lengths, those will be more or less the same, right? Here upwards, here downwards. But the effect of the lone pair, that will be added to this with the NH3, because the dipole moment of the direction of the lone pair, is with the same direction as the resultant of the bonds. It will be added then. The lone pair will be added to the resultant of the bonds. But in this case, here lone pair is added. But here the lone pair will reduce the amount of dipole moment appearing with the bonds, because those are with opposite directions. Here the lone pair effect is towards upwards, the bonding, the dipole moments of bonds towards downward. So net effect, we have to consider net effect. If you have to consider net effect, the net effect or the net dipole moment would be like this for the NH3, but here it would be like this, some decreasement due to the lone pair. So ultimately we can say the net dipole moment is like this, and here the net dipole moment is smaller, right? This is net dipole moment, mu bar. So the net dipole moment of NH3 is larger than the net dipole moment of NH3. So we can say polarity of NH3 is greater than the polarity of NH3. Greater the net dipole moment, greater will be the polarity, right? That is the idea. So like this, due to the effect of the lone pair, we can comment on the relative polarities of NH3 and NF3, right? Got the idea? So draw this one, this picture, and complete the note. Complete the note. Right now? Okay. This is how to compare the NH3 and the NF3. Effect of the lone pair matters here. As with the bonded pairs, the resultant is almost the same. The effect of lone pair decides which is with a greater dipole moment and which is with a small dipole moment. That will ultimately decide the polarity of the molecule. Right? Okay. That is the idea. Right? Right. Okay. So let's consider, right, few molecules. Let's consider few molecules and decide whether those are polar or non-polar. Right? Let's consider some examples. Right. Let's discuss about the polarity of carbonate ion. Polarity of CO3 2 minus carbonate ion. this concern. Let's do some working to come up with whether the carbonate is polar or non-polar. Right. This is how we are to decide that. If they have given you a species and they have asked you to comment whether it is polar or non-polar, this is how you are supposed to derive that. First, these are the steps, right? First, draw the naturally existing species with the correct shape. Then mark all the mark dipole moments with all the covalent bonds. Then take the net dipole moment. You may need to resolve the dipole moments from here. If, right, let's say take it as mu bar. If mu bar is equal to 0, then your species is non-polar. If the mu bar is not equal to 0, then the species is polar. That is how you are supposed to examine whether a species is polar or non-polar. Right? Let's do these steps to our molecule CO32 minus. CO32 minus. First, draw the naturally existing species with the correct shape. So one can draw the carbonate molecule like this. It's going to be the carbonate molecule, the Lewis structure. But naturally existing form is not this. So the double bond could be here, here as well as here. No? So naturally existing form is actually resonance hybrid. So the properties of the naturally existing form will be given by a resonance hybrid. So carbonate, the existing carbonate will look like this. Existing carbonate looks like this. This is the existing carbon. Right? Existing carbonate given by a resonance hybrid. Right? So you are with a pi over 3 kind of a bond order, right? 1,5 bond delocalizing in 3 places, right? Okay. The first thing is done. Draw the naturally existing species with the correct shape. So naturally existing species is like this, right? The resonance hybrid. Then mark dipole moments with all the covalent bonds. Let's mark. Because CO bond, the oxygen is negative. So the electrons will attract towards the oxygen. Like this. Carbon is your positive pole. This atom, while the oxygen is your negative pole. The great atom. So that is how you are supposed to mark the dipole moments with all the 3 bonds. Right? Mark dipole moments with all the covalent bonds. That is done. Next, take the net dipole moment. So you will clearly see these three bonds are equal, and this can be considered as a perfect shape. This can be considered as a perfect shape, no lone pairs, and all the three bonds are equal. So it's a perfect shape. So with the perfect shapes, the dipole moments will cancel off, giving you a zero net dipole moment. So the net dipole moment is equal to 0 here. So the species is non-polar. This species is non-polar. So carbonate is non-polar. The carbonate 9 is kind of a non-polar stuff. The symmetric electron distribution can be seen with the carbonate. Even though it is 2 minus in charge, it's a negatively charged particle, still its electron distribution is symmetric. Its electron distribution is symmetric. That is what it says. Yes, minus 2 charge may appear, but that electron distribution is symmetric, right? That is what it means by the situation of non-polar. So carbonate is kind of ion which is non-polar, right now? Okay. So that is all about the polarity of molecules. So you clearly see here, right? To decide the polarity of a molecule, not only about a bond, but when deciding a polarity of a molecule, the electronegativity, that is how the dipole will be marked according to the electronegativity, and the shape of the molecule, that means the geometry of the molecule, right? All matters, right? When deciding the polarity of a molecule, the electronegativity as well as shape both matter, right? That is why the topic says the electronegativity, geometry, and the polarity of molecules, right now? Okay, that is all about the polarity of molecules, our main discussion today, right? So some few questions are there with your workbook as well. Just do them. First, draw the correct naturally existing species, then mark all the dipole moments of them, and then decide by taking the net dipole moment. That is how you are supposed to come up with the polarity of a molecule, right? So let's wind up at this stage about this topic, right? Then goodbye then. See you next week.